They've already crossed 100.
Shall we start? Vinay? Okay to start?
Yes.
Okay. I welcome you all again, my fellow bridge engineers, especially those who love steel bridges and design with steel bridges. This seminar, or rather, let's say this series of webinars, are specifically focused on steel bridges. And this is day 2 of the series, which is once every month that we are having these talks. This is the second one, and I'm delighted to welcome my friend Atul Bobe, one of our most renowned engineers today, dealing with the number of steel bridges, and you'll be very happy to receive this presentation, I'm sure. Welcome again, of course, to our President Vinay Gupta and our dear S.K. Puri Saab, who's the chair of our B5 committee on steel bridges. So he attends, and very good of him to be amongst us today as a panelist. My young engineer, I like to call him young compared to me, definitely Tarun Goel, another very good steel structural engineer, done a lot of railway bridges, and behind him you see the LRT that is part of his work in Mumbai. And of course, Deepika and Ruhi, our own colleagues from IAB. Welcome to you all. And may I ask Deepika or Ruhi to take over for the moment?
Thank you, sir. So I welcome you all again to the IIBE special lecture series. So this lecture series will be of a 6 months duration, focusing on steel bridges. And this is presented along with JSW. Today's session is from engineer Atul Bobe, who will be doing on the topic MG Setu with choice of steel in superstructure versus replacement in concrete. To begin the session, I would like to play a small introductory video on IIBE. So yeah. Thank you. Now I would request Madam Purnima to please present her video on JSW. Thank you.
India, a nation powered by 1 billion dreams. Dreams that we aspire to fulfill every day. Together with our collaboration and commitment, as India embraces to be a $5 trillion economy by 2025, we are all geared up to be a part of this monumental journey to usher in a brighter, better future. Together, we touch ordinary lives and make that difference. We better every day. Together, we make steel that you carve into your agri-equipment. Together, we sow the seeds of success. We make steel that gives the grit and grind to your heavy equipment. Together, we change the landscape of our country. We make steel that you beautifully mold into your automobiles, just to drive our nation on its path towards prosperity. We make steel that you transform into solar energy. Together, we steer our nation towards a greener tomorrow. We make steel that relays your transmission lines, just to brighten the future of millions. We make steel that styles your appliances. Together, we bring happy smiles. We make steel that adorns your development projects. Together, we provide shelter to millions. We touch lives, make them better together, every day. We empower communities, make them better together, every day. We nurture dreams, make them better together every day. As India embarks on its accelerated growth journey, we are firmly placed to leave our mark in it. Together, we touch millions of lives and make them better every day.
Thank you very much. Now, today's event will be moderated by Dr. Harshvardhan Subbarao, sir. So I will now officially hand over the session to him. Thank you, sir.
Thank you, Deepika. I would like to first welcome, of course, amongst us, our sponsors and persons who have supported us from JSW Steel. And they include Mr. Ulabje, Mr. Prasad Sawant, Mr. He was here before for a little while, Mr. Vinay Pandey. So thank you, sirs, for being with us and supporting the IAB. And it's always good to have you with us, and your encouragement is very much appreciated from all of us bridge engineers in the audience, as well as those who are here on this panel. It's my pleasure once again to say a few words about my friend Atul Bobe. Atul, if you want to put your first slide on and start your screen sharing, I will. Atul really requires no introduction amongst the Indian bridge engineering fraternity. In fact, he works internationally a lot too these days and has been for some time. He did his master's from Ann Arbor, Michigan, a college which I too went to at some point for my master's, maybe a year apart. And Atul came back, joined his firm SN Bobe, and built up this firm to what it is today, and now joined hands with an international group called TPF. And that company now is TPF, which he heads now in India. That firm is doing all kinds of structures, including arches, bridges of different types, cable stays, skywalks, every type of possible bridge, apart from various other structures in which they're also involved. So he has given talks on this fora, which have been very, very much appreciated before. Today, he will be speaking on a topic which is very, very critical for all of us, about a bridge which was built over the Ganga at Patna, and how that bridge, having suffered huge distress over its time, was put to a repurpose. That means there was circularity addressed, and after, I wouldn't say the end of its design service life, but end of its usefulness, maybe, that structure was rehabilitated in a way which gave it a new lease of life. And that was done, that new lease of life was done with a steel superstructure option. And Atul will be speaking to us about that today. Go ahead, Atul, yours.
Yeah, there you go. So thank you very much, Harsha. Of course, it's always a pleasure to be on a session that is moderated by Harsha, a very close friend of mine and a colleague in the consultancy profession, and a fellow bridge engineer as well. Also, a very warm welcome to all of you, all the participants, all the members of IIB, the sponsors, everybody who's keen to listen to what I have to say. I've titled my presentation Rehabilitation of Mahatma Gandhi Setu. Now, actually, it's not a rehabilitation. It's the replacement of the superstructure. But when we started this job, it was titled Rehabilitation of Mahatma Gandhi Setu. And of course, the national highway number that you see was the number that was the erstwhile number of this national highway when we started this job. Just to give you an idea of the timeline of this particular presentation, this DPR, as we call it now, this DPR that you are going to see was first awarded to us in the year 2012, a decade back from now. And we took 6 months or 7 months to come to a conclusion of this DPR and to send a recommendation to the ministry. At that time, we were working for NHAI, and then, of course, later the work was transferred to the Ministry of Road Transport and Highways, who took the project ahead. So let's, without any further ado, let's begin the presentation. And these are the contents of, and the way that I want to present this is the brief history of the bridge, salient features of the bridge. And when I say brief history and salient features, remember I'm talking of the old bridge. Condition survey and findings of 2012, that's the year in which I mentioned we did the DPR. At that time, there was a distressed span, number 44, and there were solutions for that span. And for all the other spans, what were those solutions and what were finally adopted and are being implemented now, even as we speak. I'm going to spend a substantial part of this presentation explaining to you the history and the salient features of the bridge. Normally, it is said that people who don't learn from their history are condemned to repeat the mistakes in the history. So one of the objectives of this first part of this presentation is to make sure that you know the history of this bridge, which was an iconic bridge of its time, which was a most innovative design in concrete at the time when it was executed. So just for those people who don't know where the bridge is, this is just on the border of the Patna city. It's the national highway connecting the north of Bihar to the south of Bihar. And at one time, this was the only connection between North Bihar and South Bihar. And if you had to go from Patna to anywhere in the north, or if you had to travel from Hazaribagh in the north to the south, then you had to cross this bridge. So this was a very, very critical connection on the national highway. So this is a brief history of what the bridge was. So the construction of this bridge was started by Messrs. Gammon India Limited in the year 1972. In 1972, the bridge construction on the upstream side, this was a 4-lane bridge divided, well, it's not a divided carriageway, but there were two independent superstructures that were constructed. So the bridge construction on the upstream side was completed and opened to traffic in 1982. It took 10 years. The downstream side took another 5 years. So a total of 15 years were spent in constructing the bridge complete. Unfortunately, the bridge started showing distress around 91, 92, immediately after it was about 4 or 5 years after it was opened to traffic, immediately on the expansion joints to begin with. In 1996, the section on which the Mahatma Gandhi Setu lies was declared as National Highway 19. And the maintenance of this bridge was with the state PWD till 2011. under which various reports on the state of the bridge were prepared, the condition surveys were done, external pre-stressing and change of central hinge bearings in some spans was already undertaken at that time. Serious defects and failures in one span, span number P44 on the upstream side, was observed in the year 2011 in the month of March, and the flow of the traffic had to be restricted because the span had undergone a complete failure, and therefore people could not use the upstream bridge. So all the traffic was diverted only on the downstream side. So that's in very, very brief what this history of this bridge. But the salient features of the bridge will tell you why this was an innovative bridge. It was a bridge which was at one time, when it was constructed, the longest bridge in India, 5.575 kilometers. It had 45 spans of 121 meters, with the two end spans, the two last span being 63.53, which had suspended spans of 7.1 meters on sitting on the articulation on both ends on the abutments. There were viaduct spans on the Patna end, almost a kilometer, 965 meters to be exact. There were 28 numbers, 35 meter almost, 34.46 meter spans with simply supported PSCI girders. The carriageway width I already mentioned was a 4-lane bridge, so it was 15 meters, and it had a central verge of 0.75. It had footpaths on both sides, railings, service ducts. It had service ducts running underneath the footpaths. The lighting was on the central verge, and both carriageways had separate superstructures supported on a common pier and foundation system. The foundation system for this bridge was wells. So they were well foundations. The piers were hollow D-shaped RCC columns. The superstructure, which was the most innovative part of this bridge, was in precast segmental pre-stressed concrete box elements. The depth of the box, because this was a conventional cantilever construction carried out at that time, the depth varied from nearly 8 meters on top of the piers to only 2.16 meters near the pre-ends, where there were central hinge bearings. Now, this particular design with free cantilevers standing out and only a central hinge bearing at the end of the cantilever was used in several places at the same time with similar spans and similar designs, but this one was one of the early applications of this particular design. So the expansion joints were finger type MS joints. For the moment, bear with me with the English, you will see pictures of these very soon. The vertical clearance was nearly 11 meters at the pier location in the springing of the box, and of course it was much, much more in the center of the span because the depth varied from 8 meters to 2 meters. So you had almost 16, 17 meters of vertical clearance in the central portion of the bridge. The horizontal clearance was 114 meters. I mentioned to you that 125 meters was the span. So you had well foundations there, which occupied part of the space. So you had horizontal clearance of 114 meters. Now, this is a typical picture of how the bridge was. And you will see that these were precast, segmentally cast box elements put together by pre-stressing. And then there was a free cantilever beyond this on which there was a central hinge bearing. This is the last span going towards the Patna end. This is the pier number 44, 45, 46. That's the cross section. And if you see the depth I mentioned, this varies. That there's one box on the upstream side, one box on the downstream side. You had the footpath, and then you had these cable trays carrying utilities running underneath the box. They were attached to the box girder, and they were running all through the length of the bridge. So you had these 15 meters of cross section, which had 750 meters as the central verge as part of it. And also the footpath, which sprang out from the box, was different from what we do now. Now, of course, you know that we extend the slab all the way through and we create a hollow beneath the footpath. So this was the typically fly-wing kind of a footpath that was constructed in reinforced concrete. That was the construction method. I already mentioned to you that there would be a free cantilever, and then there would be a central hinge placed here, making it a propped cantilever kind of a design, making it quite economical. And that, of course, now we know that this is the most conventional way of doing balanced cantilever construction, is to use form travelers cantilever construction gantries. You have the temporary tower with vertical pre-stressing holding on to the towers, the pier table as we call it now. But you had the pier segment on top, which was in situ, and then you had the precast segments climbing out with the form traveler. That's the principle of the cantilever construction. Very simply put, you put cables in each and every segment so that you can hold the cantilever in place till you reach the end of the cantilever, and then you place the hinge at the center. That's the theoretical functioning of the hinge. And like I mentioned, you have the propped cantilever effect coming into play. So you have lowering of bending moments, you have adjustment in the shears. So you get benefited in terms of economy in concrete and steel that you would use. Now, what happens if that hinge does not really function as a hinge, which is where the problem on this bridge started? The hinge started giving problems. And this is what happens when the functioning of the hinge becomes not so ideal hinge condition. You have differentiation reacts, and then your structure starts carrying more moment than what it was designed for, more shears than what it was designed for, and then it starts showing distress. So functioning of the hinge, deflection and moment, of course, this is pretty simple. And of course, if your hinge is not there, what happens is there is vibration on the structure, which can lead to failure. So just as an example, we tried to see how much a joint of the bridge would move, considering that there is an 8 millimeter movement in every 5 minutes due to a live load. So if the movement in 1 hour is 8 millimeters, then the live load is 96 times. It has 96 millimeters of movement because you have 8 millimeters every time. So the total movement is 96 movement in a day, 2,334 movement in 1 year, 851910. Movement in 20 years, if you consider differential settlement of 25, seismic effect of 25, loss of pre-stress 25, you will find that your cantilever travels 17 kilometers in a short span of 20 years. Now that's quite phenomenal, isn't it? Nobody would imagine that your expansion joint is actually traveling that kind of distance in the life of the structure. Well, this is not even the life of the structure, it's just 20 years. So that was an eye-opener for us. I'm going to take you through condition survey and findings of the year 2012. What we found at that time, pretty shocking, as you will see. So of course, the good thing is that because the bridge was only 15 years old or 10 years old, the as-built drawings were fully available with the department, which is generally not the case. But fortunately, the local PWD, the state PWD had the full collection of as-built drawings. They didn't have a collection of the designs, but fortunately, all the drawings were in good shape. So to assess the existing status of the bridge, a physical inspection of the bridge was carried out. Now imagine you're carrying out the inspection inside of the bridge. The bridge is 5.6 kilometers on either side. So you have to inspect 12 kilometers of the box inside of the box. And what we found inside the box was pretty shocking. There was water accumulation at a lot of places. There were all kinds of rubbish lying inside the box. Sometimes the boxes were stinking because of the water accumulation and so on and so forth. Also, some of the boxes were cleaned because they were already externally pre-stressed. The work was going on. And so they were cleaned because of the contractor who was working on the external pre-stressing. We had to assess the traffic plying on the bridge. And remember, like I said, the bridge was only open for half its width. So all the traffic was plying only on this part. Heavy vehicles were banned on the bridge. So they had to take a detour of almost 100 kilometers to go from North Bihar to South Bihar. While assessing the overall health of the bridge, we had to carry out strength assessment by all kinds of testing that was available, including testing cores from the concrete. We also did a deterioration assessment by testing permeability, carbonation, and chemical attack on concrete. And the assessment of a permanent deformation was done by a simple total station survey because all the cantilevers had to be checked for permanent deformation. This was the status of the as-built drawings. As you can see, they were all blueprints. At that time, you didn't have AutoCAD, you didn't have digitized drawings and so on and so forth. So you had blueprints of almost all drawings. And we created a digital trail, a digital archive of all the drawings that we could find, so that this is now available for posterity in the ministry. We gave them all the drawings fully digitized and archived in a database. Of course, now at this stage, it is of no use because you know that the bridge has undergone replacement of superstructure. So the drawings are there now only for history and for people who would want to see how bridges were built in that time and how this bridge was built in its earlier avatar. So there you have it. That's the substructure and foundation details. And you will see that all the reinforcement details in pretty much everything that you would need, a bar bending schedule, everything was available in good condition. So while inspecting the bridge, condition survey of the bridge, we had to check for serviceability, damage to components, visible signs of distress, closer examination of components which indicated visible signs of distress, and of course, documenting the status by taking photographs and doing video shooting. So how did we do this? From the deck top, inspection of wearing coat, railings, median footpaths, service ducts, and light poles. This is obvious. From the ground, for conditions of piers, well cap, and box girders. From suspended platforms for selected spans. So we randomly chose spans and we had suspended platforms placed there. We had no mobile bridge inspection units at that time. Of course, the Bihar government did have 2 units available, but they were almost defunct. So we had to make do with suspended platforms. And like I mentioned, we walked the entire 12 kilometers inside the box, a pretty harrowing experience. And I'll tell you why. And then we had ladders and scaffolds erected inside the box so that every square inch of the box could be inspected. Central hinges of all the spans were also checked and inspected. The exposed deck slab portion where the bearing coat was removed was also inspected. So we had bearing coat removed in certain locations where we had a doubt about the deck slab portion. Expansion joints and deck slabs near the joints were fully inspected, and portions of the box from inside showing visible signs of distress was further examined. So while documenting the details, all central hinge bearings at both webs in both downstream and upstream carriageways were documented. Other areas considered significant, such as soffits of top slabs of the pier segments, members showing visible signs of distress, deformations such as visible cracks in top slab, bulging of concrete, deck slab soffit, etc., were all photographed, and this was made available. In terms of video shooting, all expansion joints were shot. Video shooting was done. The railing on both sides of bridge in minute detail was also captured. And central hinges in these particular spans were captured because they were showing large distress and the spans were showing large deflections. Now I will show you a few pictures of what was. As you see, this was just a picture of this expansion joint on piers 41 and 42. If you see the movement of this span, this was one of the better behaving spans. It was moving only by 10 to 12 millimeters. The hinge bearing here had nearly failed, and the span was dropping down, and the vibrations were uncomfortable when you stood here. And of course, remember that heavy vehicles were banned on this bridge. So you saw only motorcycles and light vehicles crossing the bridge, and the deflection was already very, very severe when you stood on the cantilever. So this video just demonstrates to you the level of defect of the serviceability of the bridge. It had deteriorated beyond acceptable limits. That's the status of the central hinge bearing. Now, this is the plunger, and you see this is the base plate of that central hinge bearing. And many of these were seen to be broken or tilted beyond repair. It was impossible to repair these bearings because you have to take care of almost everything. So this is, you can see, this is the expansion joint between piers 18 and 19 on the upstream side. This is the right-hand side carriageway, the carriageway right side hinge. So you can imagine documenting hinges of this. And why I said it was a nightmare walking inside the boxes, because the boxes were vibrating uncomfortably when you used to walk inside the box. The soffit of the box was in the shape of an arch because it went from 8 meters to 2 meters. So you are already doing something like a huge mountain climbing, because in 100 meters, you are climbing 6 meters. It was pretty uncomfortable doing the inspection. Now that's the damaged expansion joint on pier 43, 44. So this particular span had started to show distress. This was one of the first spans that started to show distress. And you will see that the expansion joint here has disappeared. It's fallen off. The finger joints here are in place, but look at the gap that's created. The hinge had failed, and the joint had also failed in this part. It was almost near to failing here. The bearing course had cracked at all locations, and this was almost unserviceable. That's one of the reasons why this span was stopped to traffic, and all the traffic was moving only on one side of the bridge. That's another span, 36, 37. Now imagine what happens when a vehicle comes from this side and traverses from left to right. Lot of cases of puncturing of tires has been reported on these bridges before we started working on this. The gap between two slabs, you can see the gap here on the curve. It's nearly 50 millimeters, and heaven help the person's bike that hits this kind of an obstacle on the bridge. And this was happening at every expansion joint location. Now, this is just an example. 36, 37 is the joint number. This is what had happened to railings on both sides. Because of the excessive tension that got transferred to these railings, the railings had started to develop cracks. The vertical posts as well as handrails had cracked beyond repair. The railings were broken. They had fallen off into the river. And you see these gaps created because this is where the post was and the railing fell off. So here's some bamboos were attached so that people don't fall off the bridge. On the footpaths, you see these suspended platforms placed, which were being used also for external pre-stressing by the contractor. Some of these holes we later used to put our own suspended platforms so that we could inspect the bridge. That's how extensively the wearing course was damaged. So you can see how expansion joint, you can see the gap between the two spans. You can see how expansion joint had come off, and you can see the amount of distress on the wearing course. So this was really beyond repair, even in 2012 when we came to the site. Oops. Some of the things that we saw on the inside is there was bulging of concrete for the walls and top slab. Rusted sheathing, you could see the rust spots, and in some location the gaps were so large you could put your hand through and touch the cables and you could feel the cables moving. It was that scary when you went inside. You see these exposed sheathing which had completely rusted by the time we came into picture. Some spalling had started to take place, and it was pretty scary. Once you started to go inside, you see the water marks, so the leakage was happening at these locations. And mind you, this is not the location of the joint of between two segments. This was on the top slab of the segment. So it was pretty scary. For the central hinges, the vertical plates behind hinges were seen detached from concrete and hanging in slanted position. I showed you a picture already. The vertical plates at a lot of locations had sheared off and torn off from the bolts. Plungers had cracked, and damages to plates below plunger and to concrete was extensive also. That's how it looked. The plunger, the plate has completely come off. The bolts have sheared. The plate has completely come off. It's a dysfunctional central hinge bearing. That's another one that is tilted. And the plunger is still there, but it's not functioning anymore because the bolts have sheared off. More pictures of the same. You can see the crack, the shear crack on the plunger. That was the state of most of the central hinge bearings. That's another one that's near failure here. From the bottom plate, it is sheared off. Now this span number 44, if you see the gap here, this had dipped by nearly 1.5 meters. So this span had completely failed. There was no way we could have done anything to this span when we actually came to the site. This span had already failed. The bridge was closed to traffic, and you see what's happened to the portion of the slab that was holding the expansion joint. That's the utilities that were taken over to the other side, and that had also failed. Now, of course, I'm not going to talk too much about the NDT that we did, but suffice it to say that a lot of ultrasonic testing, concrete cores, et cetera, was done to ascertain whether the concrete at least had its strength or not. That's a sample of what tests were performed on a span. So what we found, and surprisingly so, is that the concrete, which was 30 years old, was still very good. Well, not very good, but in fairly good condition. The results were in acceptable range of acceptable results. The core strengths also indicated and corroborated the same thing what the USPV was showing. Carbonation, only surface carbonation was observed. And so this was also considered acceptable. So all in all, the concrete by itself had not failed. pH values were showing strongly alkaline concrete, offering excellent protection to reinforcement steel. Chloride content, much less than permissible chloride. Very low chloride ion permeability, and so on. So as you see, the concrete was good. So chlorides and sulfates in concrete were below permissible limits and has very low chloride ion penetration. Concrete is alkaline. Concrete is uniform, and quality of concrete is okay. Carbonation is limited to surface, not really transferring itself inside. The concrete strength was unaffected even after several decades of use. Now, this is a summary of what we found. So well foundation did not show any apparent distress. Well caps, which were fully accessible, of course, we could not inspect the inside of the wells, and of course the outside of the wells also, which were either in water or inside sand. So they were left to their own devices. We did not inspect them by doing anything much. But whatever was accessible, almost all well caps and a part of the wells were accessible. They were inspected, they were checked. There were no foundation settlements. Fortunately, like I mentioned and showed you, we had the as-built drawing, so we knew the levels. So we had cross-checked these and there was no change in those levels. Abutments and piers also did not show any visible distress. We also checked the concrete quality, found it okay. Superstructure, unfortunately, you have seen showed considerable deflections, although the condition of concrete appeared good. The central hinge bearings were damaged beyond repair. Signs of imminent failure of hinges was seen in many spans. Expansion joints were damaged also in many spans and separated due to relative deflection of adjacent spans. And corrosion of sheathing ducts in deck slab was observed almost in all spans. So the failure of central hinge, as I showed you in one of the earlier slides, the central hinge is supposed to take the loads of the SIDL and vehicular live loads. The dead load deformations are presumed to have taken place before the hinge is installed. So probable causes for failure was defective installation or maybe the fatigue due to repetitive loading and movement of the hinge under live loads. Because remember, like I said, this was one of the very early applications of a central hinge design in India. It was one of the most innovative concepts at the time when it was implemented. Of course, a lot of other reasons: quality of material, design of the hinge itself, actual deflection being in excess of the design value, deflection of girder due to loss of pre-stress, and of course, everybody knows at that time, we now know that the loss in pre-stress was always underestimated. And of course, the last point was that overloading on the bridge could have caused excess load on the hinge. Now, this is something which could not be corroborated because when we actually went to the bridge, there was no overloading because there were no heavy vehicles permitted on the bridge. Of course, it is not just one factor, but a combination of all these factors which could have contributed to the failure of the hinge. Now, the distressed span number 44, what could we do to that span was the question that had to be answered. And now, you know, of course, you have seen this slide. This span had large deflections besides failure of a cantilever which had to be replaced. So the first thing that we said is that we had to deconstruct the span and then to reconstruct it. This was one of the solutions that we were looking at. A segment launching girder would be erected in 2 spans and supported on pier segments. So the girder had to be 240 meters and not 120 meters. Each segment would be strung by HT bars and trolleys supported in launching girders. And after de-stressing the original cable, the segment would be cut loose individually and removed. That was a plan to remove this span, because this span we decided had to be removed. We had to do regirdering of this span. So the answer was to erect a 2-span launching girder or a de-launching girder. There you have it, a 2-span de-launching girder. We would drill hole through the segments for the suspenders to be provided. We provide suspenders. So we are following an exact reverse process. Instead of launching the girder, we are de-launching the girder. So you would do exactly this, all the steps in reverse as you would do today to do a segmentally constructed box, launching a segmentally constructed box. And then the idea was to lower them onto pontoons and remove the span completely from its location. Move the de-launching girder to the next span and also remove this span. Okay. And then we would sort of repeat the same process for all spans. So once the concrete was removed, the idea was to place a truss on top of the already removed box. Now, here is the crux of the problem. Maybe I'll talk about this a little later as we move ahead. So how would we construct this span? So, okay, these were the several options that we had. So let's talk about these. We said that the first option was the do nothing option, which is the individual segments which we had removed could be reused. Or if they were found unfit, discarded, and only those segments which could be reused and new ones could be cast for those which were discarded. This was one solution. Newly designed low relaxation cables. Now remember that this bridge was designed with the old wires and strand systems. So the low relaxation strands were not available at that time. So we said if we use newly designed low relaxation cables, we could insert those, and we could use gluing with the new technology that we currently use, let's say the epoxy gluing of segments, we could do that. Discarded segments could be lowered on pontoons and new segments could be lifted up from there. But this had a major problem. One of the problems was that if we did this, the amount of time that we would take would be enormous. So we said, if we could use a steel truss girder for replacement of this particular spans, we should and could do it. And the central hinge bearings for all the remaining spans could be reinstated with central hinge bearings of modern design. This was the first thought process that we had for the distressed span only. That's how it started. Then the question was, how do you replace all the other spans? So the first thing that you have to bear in mind is that when we were thinking of replacing these spans, we had to consider the serviceability of the bridge and the structural safety of the bridge components which were in distress. With these 2 points in view, we started looking at alternative solutions. Since the deflection of most spans were considered to be in the elastic range, the first thing we said is that it was desirable to reduce the load to be able to reduce the deflection as far as was practicable. Now, what do we mean by that? So for immediate relief, we said we could do 2 things. These measures could be implemented immediately without much difficulty and could result in much needed relief for the structure. Now, the structure was already highly stressed at the time when we started looking at it. So this was immediate relief. And then we had to do a step 2, which was the permanent solution. So these are the measures that needed to be implemented to extend the balance life of the structure to the maximum possible extent. Everybody agreed that even though the design life of the bridge was, say, 70 years or 80 years at that time, the bridge was not going to reach its design life. So the idea was to see how much we could extend the balance life of the structure. Remember at that time when we were studying this bridge. There was no proposal of a new MG Setu or a Kachi Darga bridge or a Ara Chapra bridge or whatever. The whole solution was hinging on repairing and putting this bridge back into service as fast as possible. So what do we do to provide immediate relief? One of the solutions was to replace the existing 110 millimeter thick bearing cores with a simple membrane and 25 mm thick bearing cores. This would give a substantial relief in terms of stress in the superimposed dead load to the span. Also, to reduce dead load on the bridge, we suggested demolishing footpaths and railings for all spans. And instead of the RCC railings, put in place metallic bearings, which were lighter. And they could be anti-crash barriers, the new ones that we have. And channelizing traffic in center of the carriageway by placing bollards so that the traffic doesn't travel eccentrically. We open both carriageways to traffic and only one lane of traffic on either side would be operative. So we would put the bridge back in service, but we divided carriageway and individual carriageways available to traffic. With some restriction and some policing, this was also agreed by the local administration. This could be done even before implementation of any other strengthening measures. It would be easier to implement strengthening measures if the superimposed dead load was reduced. This was one of our early recommendations. So that's how it would look. You would remove the two footpaths that were cantilevered. They were adding dead load to the bridge and that to an eccentric dead load, and replace them with simple anti-crash barriers, the steel anti-crash barriers, and then reduce the thickness of the bearing cores. That would reduce substantial amount of weight. That's how it would look with these bollards. So you had a 5 meter carriageway left in place. You had 1 meter on either side, which would be defunct, and we would use only 5 meters. So one lane of vehicles and maybe 2-wheelers or 3-wheelers could use the bridge simultaneously. So we had 10 meters of carriageway available. So one of the immediate relief advantages of this immediate relief was reduction in superimposed dead load by almost 2.5 tons per meter, leading to a bending moment reduction of nearly 4,500 ton meter, which was 10% of the total bending moment. So reduction in stress was of the order of 20 kg per cm square. So substantial reduction in stress. Also, it would reduce eccentric loading and transverse vibrations. The video that I showed you was not perhaps very clear, but the span was moving up and down and in the horizontal direction as well. The disadvantages of this was the reduction in effective carriageway for traffic, and traffic diversion would be needed during implementation. This was one of the most critical items for the local administration. We came to permanent solutions, and like I mentioned to you, we looked at several solutions for this. One was replacing the central hinge bearings with modern design central hinge bearings and externally pre-stressing the spans which had not yet been externally pre-stressed. Almost 40–50% of the spans had been externally pre-stressed by the time we looked at the bridge, but we thought we would also externally pre-stress rest of the spans. Replacing CHBs with pre-stressing or other alternate means to connect the superstructure and convert it to a continuous portal frame. So this was the solution number 2. So what we thought is that if we converted the cantilever construction into a continuous portal frame by removing the central hinge bearings, adding pre-stressing, which would take the shear and the moment created, then we could convert the superstructure into a continuous portal frame. This was the second solution. The third solution was to strengthen the cantilevers externally with steel trusses or internally with fiber and steel wrapping. So it was a combination of fiber or steel wrapping inside so that the segments which had gaps, segments which were showing the ducts which were getting exposed would no more get exposed. They would be covered by fiber wrapping. And externally, we would place trusses or steel girders, let's say composite girders, which would be able to carry the load partially. Another solution was to erect new piers under the cantilever tips and introducing bearings for all but the navigational spans. Now, this was also a solution which was simulating a propped cantilever design, which was the original design. So we would have had to erect something like 50 and 50, 100 piers, one in between every span, so that the cantilever tips would be supported. The last one, the fifth one was to dismantle the existing superstructure and replace it with a new superstructure while retaining the substructure and foundations. And the last one was to construct a new bridge at an alternate location parallel to this bridge near Kachi Dargah. So the Kachi Dargah bridge, which is now under construction, so we carried out a sort of a pre-feasibility while saying that if we had to absolutely have the same level of serviceability and service life of the structure, then the best thing was to dismantle this entire bridge or just let the bridge be and abandon it and construct a new bridge at a location parallel to this bridge near Kachi Dargah. A bridge parallel to the MG Setu at the existing location was almost ruled out because on the Patna end, there were a large number of structures that were existing. And land acquisition was not easy in 2012. The new land acquisition bill was not passed. So it wasn't easy to acquire land in that area. These were the 6 solutions that we looked at. I'm going to show you also, yeah. So this is the first solution, external pre-stressing and replacement of CHBs. I'm not going to go through too many of these details because it's a long drawn presentation if I start talking of central hinge bearings, because this part of the presentation talks about, yeah, these are the new generation of central hinge bearings which came into play after the first lot, first generation that we had used in the MG Setu, the first MG Setu. So you had all these solutions also available. The second solution, like I mentioned, it's a combination of the second and third, where deflections were large, more than 25 millimeters, where we needed an alternate solution, and hence the following options were studied. Can we make the spans continuous, making one span continuous, making multiple span continuous, etc., etc. Because we would establish continuity, large moments would develop at mid-span, where there is a disconnect now because there is a hinge bearing. This will be required to be connected. And also moments on piers would increase as compared to original design. And what we found here is that the girder section was inadequate for the large bending moments created at the disconnect. The girder depth there was only 2 meters. So almost 100% of the moment and shear would have to be carried by the extra pre-stressing or the extra steel that we would have to put. So we dispensed with this solution. So the options for creating connection at the disconnect was post-tensioning over the disconnect, PT slabs, PT bars, but the depth and space was inadequate for the amount of PT that we needed. A stiffening girder connecting the 2 cantilevers, what today is being called a needle beam, is what we had suggested in 2012. A stiffening girder connecting the 2 cantilevers leading to a complex structural configuration. Also bringing the 2 cantilevers to the same level of deflection was an unresolved issue because almost all places, the 2 cantilevers had dipped unequally. We found also that the piers would need strengthening, and this is possible to be executed without much difficulty. The foundations would also require strengthening, and this was almost impossible to execute. So overall, we decided that this was difficult to implement as a solution. The next one, so where spans with large deflections and replacement of central hinge bearings, it will not be adequate to extend the life of the bridge. Following solutions were proposed. For span P29 non-navigational span, remove the hinges, add bearings supported on newly constructed pier, thus reducing the span to only 61 meter. But it leads to positive bending moments inside the box. We could manage it by strengthening the box. Navigational spans piers cannot be constructed, and hence various other options were studied. So this is one of the solutions, is to add a pier here and put a bearing below it so that this span becomes a propped cantilever, which was the original design, more or less. For the navigational spans, what we thought of is to put steel girders inside these, make this box girder completely defunct, which were highly damaged, highly deflected, but we needed them so that the wearing surface and the top slab could be retained. So we designed simple steel trusses which would go under this. And okay, the slab would span between these trusses. This was a solution that we would use for navigational spans. Another solution was to put in an extra dosed solution with trusses inside it, which would carry the box. Yeah, I don't know if you can see this line. That's the box girder line. But we would put trusses instead of composite spans, and we would extra dose it. And then you would need only 3 trusses instead of all those trusses that you saw in the earlier span. For the navigational span, this was another solution that we thought of. This is the cross section at center. We put additional trusses, we brace them, and we add load. We take the load of the box at the center with these trusses. Of course, reconstruction is one of the solutions that we looked at. And when we looked at reconstruction, now you have seen the progression of how we came to the logic of reconstruction of the superstructure. So we have looked at several other solutions where we have tried desperately to keep the bridge as it is with minimal dismantling. Why were we doing that? Because Ganga is a very sensitive, environmentally sensitive river. And the idea of putting debris inside the Ganga while dismantling the superstructure was not a very enthusiastic idea at that time. We were asked to refrain from putting dirt on inside the Ganga unless it was absolutely impossible to do anything else. So the 5 solutions that you have seen before this one were with a view to see if we could save the bridge without dismantling it, and to see if we could do it. But once we came to a conclusion that none of those solutions would extend the balance life of the structure, we had to come up with a solution which would have the same balance life as the substructure had, because the substructure, in our opinion, had the complete design life, let's say 80 years or 100 years. If we had put in place a solution for the superstructure which had anything less than that, it would be doing injustice to that structure. So one of the logic behind the reconstruction of the superstructure was this, is to come up with a final solution which would have the same design life and the same service life as the substructure, maybe 100 years, maybe more. So what we did therefore is that once we had established that the concrete is of good and consistent quality, especially in the substructure, there was no deformation, there was no scour, there was absolutely no problem. We came to the conclusion that only the superstructure would be replaced. The proposal was to therefore reconstruct only the superstructure. Deconstruction would be needed and a method was evolved for this. You have seen this method earlier. This is what was proposed. A de-launching girder was proposed. And the reconstruction could only be with the sealed superstructure because we wanted to reduce the time of construction. So it had to be fabricated elsewhere and launched on site using only one side of the bridge so that the other side of the bridge could be kept open for traffic. There would be blockage of traffic on one side of the bridge, which was inevitable. And this was accepted by the administration as well, that this was something that had to be accepted if they wanted a new bridge. So I'm not going to run through this. You've already seen this. This is the de-launching girder and how we would have done the de-launching at that time. This was, okay, so this was what we had proposed at that time. Dismantle the existing girder as described in the earlier phases, which you have seen earlier also. We go to the pier head. And on the pier head, we put new pedestals. The pier head was a pretty solid section. It didn't have any pre-stress. It had only pre-stress going through. It had, of course, a few anchor cables, but they could be removed completely. Construct pedestals on the pier head to support the through truss that we wanted to be placed. And then erect a truss on top of the segment so that we could match nearly the same FRLs of the existing bridge. Of course, they did not match the existing bridge. We had to slightly raise the FRL because of the bottom boom of the truss. And it was mandated that we would be able to raise it by about 1 meter because on the approach side of both ends, fortunately, we had spans which could be lifted through that 1 meter and a shallow slope could be provided. So we said that we would erect trusses. And you can imagine this is in 2012. If you see the bridge now, the section is very, very close to what you're seeing in this particular slide. So once we had come to this particular spot, the question was, how do you dismantle a pre-stressed concrete stressed post-tension box girder? Fortunately, we had the experience of dismantling this particular flyover in Mumbai. This is also a pre-stressed concrete span. We had dismantled this in 48 hours in Mumbai by cutting it away. And so this was used as an example to demonstrate that we could cut the bridge. Here you see cutting away the slabs. I'm not going to take too much time. I'm going to run through these slides quickly. And there you see we have cut open a slab. We could completely sling it and remove the slab without creating too much dirt, without creating too much debris on site. So you see we cut open these slabs and then we had these crushers. which simply bit through PSC girders. And those people who believe that PSC girders cannot be dismantled because there's very high stress, they will crack open, compression will be there, and so on and so forth. We dismantled that myth along with this crushing of these concrete. There you see crushing of concrete. You see the cables being pulled apart. There you can see the cables here. So we simply crushed, we bit through the concrete without any damage at all. You can see we have bit through the flange, we have bit through the web, and there is absolutely no damage to the structure. It didn't fall down. You see people standing in close proximity while this was happening. Absolutely no problem. And there you have it. We had firemen dousing the crushing because it created a little bit of dirt. Then we did that. There you see we bit through the whole span and we dismantled it. We removed the girders. Here you see the cables, the stressed cables removed completely and kept aside and sold as scrap along with the. So that's the new superstructure GAD. You see how we would do it. You had the truss on one side, you had the cantilever footpath, and then you had the truss on both sides, connections at this place so that we could hold the whole thing in place together. So of course, that's the Kachi Dargah bridge, which is now under construction by another agency, by the state government on a BOT. But this bridge was therefore replaced with steel. Now, this presentation is actually talking about, this is the Kachi Dargah bridge. So I'm not going to go into that. Let me run through this presentation. And okay, so finally the solution of, I already told you what we did is to do this, is to replace the distress span, replace superstructure of the existing bridge, construct a new parallel bridge by state government, that's the Kachi Dargah. And by the time we finished this, government also agreed that a bridge parallel to MG Setu would be required because already 4-laning and 6-laning of this section was proposed. So already now the bridge parallel to MG Setu is also being constructed along with the regirdering of this bridge. That brings me to an end of this presentation, but I want to also share not a presentation, but a little bit of insight into the steel. While we finalized this DPR and submitted it to the NHAI transferred the work to North. But what happened in the meantime is JICA entered the picture, and JICA suggested that instead of using conventional mild steel, it may be better to use weathering steel. Now, weathering steel was something that was not available in 2012-13 in India. So the idea was to get this funded from JICA, and then Japanese steel would be used. With that in view, the tender was finally floated with weathering steel. Unfortunately, when we started construction of the bridge, weathering steel was not available. And we finally had to construct only 8 or 9 spans, I think, of the 96 possible spans. 10% of the bridge is constructed in weathering steel. It took a long time because supply of weathering steel was a problem. And the remaining spans, the remaining 89, 90 spans have been constructed in E450, E410 steel, and not weathering steel. So it has been used conventional steel with the weathering steel replaced by conventional steel with metallizing and painted over it for aesthetics. I think I've come to a close of what I wanted to say. Thank you very much for a patient hearing. If there are questions, I will answer them, and I hope you have had an insight into what went into selecting steel for the superstructure of the MG Setu. Harsha, it's all yours.
Thank you, Atul. That, ladies and gentlemen, the audience, I'm sure you'll agree that that was a phenomenal expose of how to go about putting in a new superstructure for an existing asset and addressing sustainability in a very, very large measure, something which we are now learning is so critical for us in our way ahead, in our future ahead. So this is a direct example of sustainability and reuse and addressing circularity, keeping what was good without affecting the environs of the river and without polluting the river, and then keeping what you have, something well built of a good life, and then trying to match a balanced life through a new superstructure, which Atul showed us about today. But how do you get to that? The story of today was, how do you get to that? you rule out, like any forensic engineer or any good repair rehabilitation assessment engineer would do. You think of the whole range of possibilities, and then you rule out those which are not, for some reason or the other, they cannot sustain. So you think of all of them, then you rule out, and then you home in on the one that is the most likely solution. So that's what he demonstrated to us today. The innovation that goes into arriving at the final item was what he demonstrated today, and showed us with reasoning how that each option was ruled out, and you home in on the only option and the constraints which require that option to be instituted. And today, that structure is now having probably completed or nearing completion for both its carriageways. And an asset has been put back, a lifeline of Patna and Bihar has been put back into use in this way, in this innovative way. Thanks, Atul. That was absolutely phenomenal. There's so much to learn from this presentation and so much innovation there. Thanks so much. May I invite the panelists, starting with Vinay or Puri Saab. One of you please go, and then we can take it turn by turn. Puri Saab, would you like to say a few words first, sir?
Okay, good evening, everybody. I think very nice presentation, very apt, because, most of the bridges, 50s, 60s, 70s, whatever were constructed, time has come that they require a lot of rehabilitation or maybe reconstruction. And as we know, the reconstruction, obviously, land issues, approach issues, and the cost issues, is very difficult for the local administration and the employer to go into. So the better option, I would not say the best option, but the better option is to, do whatever rehabilitation or retrofitting is to be done, including the, change of superstructure, because most of the time we have seen foundations and the substructures, they are by and large, if there is any kind of a distress in superstructure in 15 years, 20, 25, 30, because now the complaints have started coming within 20, 25 years of these bridges which have been constructed. So nothing happens to the foundation and substructure, but superstructure somehow, for various reasons, whether it's technical reason, one of the reasons in our country, we all know, overloading, congestion. So, there are many factors which, whatever we try to take care of during the design, but practically they are still, all our factor of safeties go away. And therefore, this, whether expansion joints, whether bearings, whether, slab, we have so many cases where the slabs have been punctured, and you really wonder what happened, that why this kind of so I think this I really appreciate the presentation of Mr. Atul today, what he has given, that considering all the aspects, the better solution normally comes out to that just change the superstructure. And I have also handled 2 or 3 cases like this. And the best is that don't go in for the concrete superstructure, just go in for steel superstructure. It is light, because even when the old bridges, if there is any issues about the live load or dead load or superimposed loads, you can reduce the load by using the steel. Yeah, 30, 40, 50 years back, we were not good in steel structures. We did not have that much, only railways had. Now we have all the codes are there, technology is there, good steel is available, it is fast, it is, even if I don't say cheaper, I would say this is also long lasting. I have not seen any steel bridge failing in 15, 20, 25 years, which these concrete bridges are failing. So with that, I will leave it to Dr. Harsha.
Thank you, sir. Vinay, would you like to have a go? Vinay, some comments from you, or are you busy? I can take unmute.
Thank you, Dr. Harshavardhan. Sorry, I was muted. Okay, good. So I'm glad that we had this presentation. Of course, at the DPR stage, I had also gone through the DPR prepared by Ms. Atul Bhobe's company, TPF, or at that time, SN Bhobe and Associates. This project or this structure or this replacement of the structure is one of the most pioneering jobs that has been done in the country so far. This must be one of the largest bridges in steel after the replacement, and definitely the largest case of replacement of a concrete by steel. And correct me if I'm wrong anywhere. Speed has its own the steel has its own advantages. That is, it is faster. It is factory made condition. You're doing most of the things in a shop yard where you have a better quality control. And as far as economics that people normally worry about, I must say that first of all, if it is not feasible to have a concrete bridge again, which was the case here, you have no other choice, you have to go for steel. And when it comes to economics, we must look at the overall economics. When I say overall holistic approach of economics means concrete is quite heavy. I'm not against concrete. I'm in fact president of Indian Concrete Institute as well. But concrete is heavy. And when you have a heavy concrete placed on our structure, our substructure, piers and all that, the earthquake coefficient does, or not coefficient, but earthquake force, it does increase quite substantially. Why? Because the inertial mass for the earthquake is the one that is superstructure on top of the pier. And that is where the weight is important. In fact, when it comes to concrete also, we try to reduce the weight to the minimum possible by using ultra thin concrete or many concepts, high strength concrete, ultra high strength concrete, ultra high performance concrete, and so on and so forth. Ideas to reduce the weight and reduce therefore the seismic forces. So that's one advantage you have. Secondly, this way old technology of constructing steel bridges. Look at Howrah Bridge, look at most of the Indian railway bridges in steel and all that. This technology must continue. You never know which natural resource may finish off. You may not find lime sufficient enough for your cement production. In some of the cities or areas, like especially in South, even aggregate is a problem. And therefore, they're going for manufactured sand, manufactured aggregates, those kinds of things. Or some artificial materials also may come in soon. So looking at all these conditions, we must sort of go with parallel technologies. And steel, of course, has been the most common technology in the past, parallel to the concrete. And at the same time, let me also thank JSW for sponsoring this 6th lecture event. And I'm glad that about 200 people are with us who are attending the lecture series today, second one. And thank you so much. Thanks to all of you. Bye-bye.
Thanks, Vinay. Thanks. Now, may I ask Mr. Vinay Pandey, a little out of turn, maybe Mr. Vinay Pandey, could you say a few words?
Thanks, Dr. Harsha, and thanks, Mr. Bhove, Mr. Gupta, Mr. Puri for nice words. It was a great presentation, Mr. Bhove, and this presentation shows how a sustainable structure can be built by steel, and which can promote sustainability, circular economy, as well as it saves the two vital ingredients. One is water and the sand. So water consumption, when the steel is used in use phase during operation and maintenance, the use of water is very, very less as compared to the concrete. As well as the sand, which is now not easily available, and many states has put a regulation that the sand cannot be mined. So under these conditions of sand and water saving, by using steel as a superstructure, it will be a great service for the environment and the society at large. So definitely the adoption of a steel superstructure will lead to such circular economy and gives a larger benefit to the society. I thank all the participants, attendees, who has given their insight and tried to promote the sustainable structure in the country for larger interest of the society. And we continue to support and move in this direction wherever needed, so that we, as a country as a large, we move towards a sustainable goal. Thank you.
Thank you.
Thanks, Vinay. Thanks so much. Tarun, you have to unmute yourself and say something.
Hello to everyone. Good evening. It was a very nice presentation by Mr. Atul Bobe. The presentation outlook was what we should not do as structural engineers more than what we should do. So what we should not do as structural engineers was the outcome of the presentations, and the failure of this bridge made us as structural engineers more knowledgeable in that sense. And the main thing which came out was we should use steel bridges, long span steel bridges for main rivers like Ganga, Yamuna, and all these North Indian rivers. So this was the outcome. Because steel is light, as the panelists have said, and if we have long spans, then because of its lightness, we can have lighter foundations and substructures. So that's what I'll say. Thank you.
Thank you, Tarun. Thank you. Venkat, you're here. You asked for this talk. Actually, you were one of the main persons to move this, Venkat.
Yeah. Thank you very much, Harsha. In fact, I missed initial presentation, but I skipped up the other meeting of mine. I wanted to hear Mr. Bobe, and I could be present for most of the times. I don't have to say it was an excellent presentation. If I say that, it will be an understatement, I believe, because he has been always an excellent presenter. Particularly, this presentation is very interesting from the point of view of sustainability, which you explained in your initial speech. Now, the sustainability is the term which is in vogue. Everybody will be looking into that. And also, there are many bridges in India, not only in India, internationally, if you really look at it, that long span cantilever bridges, because of the state of the art at that particular point of time of the creep and shrinkage model, there is a deflection at the mid-span, and the most of the cantilever bridges are sagging. I think there's a case for replacing many of those kind of bridges. I think Bobe has pioneered that. I think he should make it some sort of a patent, and he should go ahead with that. And he'll be having a lot of business, I'll tell you, all over, not only in India, internationally. And going forward, certainly, as Mr. Puri has said, that the foundations are stronger and the superstructures are becoming vulnerable to this deterioration. As you can see, though we have designed the bridges for 50 years earlier times, now for the 100 years, the bridges have started deteriorating within 40 to 50 years. 50 years also, it is especially the concrete as well as the pistis concrete bridges. Ironically, we think that steel bridges are not economical and sustainable because of the corrosion it is prone. But if you really look at the statistics, it's not so. The statistics shows other way around. If you really look at the life cycle costing and the life cycle impact assessment, if you do, perhaps the steel bridges are more sustainable, and in the long run, it may be economical also, but that study has to be done separately. And it's a classical example of how to prolong the life of the existing bridge, and also how to design the bridge, keeping the future replacement in the mind, while designing the new bridge itself. I think this sort of concept has to be kept in mind, even though we are going for a concrete bridges. The bridges have to be designed in such a way that if it is necessary for us to replace with the superstructure later, I think that has to be kept in mind. It gives a direction in that direction. It gives an orientation in that direction. In my view, it is a very high quality of the pioneering work, I should say. And as Mr. our Vinay Gupta said, perhaps it is the longest and the longest bridge which has been replaced with the steel superstructure. You know, like in the competition, perhaps maybe in the world, we do not know that, but certainly in India. Excellent presentation. And Bobesa, I just wanted to know that you said that the 10 of the spans were done in the weathering steel. Yeah. And whether the weathering steel was imported from abroad, or when you are using the weathering steel, whether you had any difficulties in fabrication and those sort of things, whether the fabrication is has to be done differently.
So it was not imported, it was Indian. The imported steel was very, very costly. If you get weathering steel from outside of India, it's very costly. But the steel that we used came from India. It came from one supplier, but unfortunately, they did not roll the quantity that we needed. Our total quantity, incidentally, for this bridge replacement is nearly 100,000 tons of steel. So given the time scale that we were on, it was impossible for us to get that kind of commitment from the supplier who was making the weathering steel. So we spent, for doing 6 spans, we spent 10 months because of the speed at which it was being delivered. The fabrication, of course, was pretty fast. There is really not much of a difference between the fabrication of weathering steel and the fabrication of conventional mild steel. Of course, the welding rods, etc., are different, but otherwise it's the same. You have to take the same precautions. You have to do the exact same things that you would do for normal steel. So there was no difference. But we finally gave up on the idea of weathering steel because the supplier was simply not able to keep pace with the speed at which we were actually wanting to do the bridge. You must know that we had only 42 months to replace the entire superstructure, out of which 30 months was dedicated to the first superstructure and 12 months for the second superstructure. So when we could do only 6-7 spans in the first 10 months, there was panic all around because you would not, you are not able to see the progress that we wanted to see. But thank God the ministry finally agreed to the change of the steel, and okay, now we have caught up with the progress, and one, the upstream side is already open to traffic, and the downstream will open in a couple of months, and we will be maybe just 3 or 4 months behind schedule, and that too because of COVID, not really because of delay that was caused in the supply of steel.
Yeah, the excellent presentation, Bobe. Once again, thank you for that. I remember to have seen those tender drawings during quoting for this job. You had given a scheme even for the,
Yes.
how to reconstruct the piers and all so beautifully in that. It was very impressive. Thank you very much.
Mr. Bobe, you just now discussed about weathering steel. There's a related question by Devjyoti Paul. I thought right away itself that can be taken up. What are the specialties of weather steel as promoted by JICA, and how is this still different from conventional steel? In case you like to reply now.
So it's weathering steel essentially is corrosion resistant, if I can call it that. What it does is it creates a platina, as it's called, on top of your surface, which prevents further corrosion. So essentially, it's creating its own anti-corrosive treatment by the nature of the chemicals that are used or the materials that are used to make that steel. That's essentially the basic difference between the weathering steel and the conventional steel. Rest everything, it's like any other steel. I mean, the Young's modulus is the same. The stresses that are permitted are the same. Everything else is the same. So it's not really much different from conventional steel.
Okay.
Okay, Dr. Ashavardhan, over to you.
Yeah, I'm just, I don't seem to be able to open the question answer session, but just to say a few words before you take that on, and I would like Ravindra to say something. Ravindra, if you're here, you might like to say a few words, Ravindra. You have to unmute.
Thank you, Harsha. It's a wonderful presentation. Of course, I joined about 10-15 minutes late, but I could get what it is. And it is a very rare kind of a case study wherein such a big span of involving this cantilever span involving failure of central hinge was rehabilitated using the steel girders. And very rarely such cases are found. And even if such things are done, they are rarely documented, unfortunately. So this is a very good presentation, and it has given a very good insight into the whole process of how to rehabilitate such a bridge and the kind of distress that was explained. It was really horrible to see that such a bridge has existed and some traffic has passed over it. The kind of steel fingers they were projecting, causing the vehicles to have punctured tires. It was really very difficult to foresee such a situation. Unfortunately, we need a central organization even for the road bridges to see that all such kinds of failures are basically documented and remedial measures are taken at appropriate level in a centralized way so that such failures are avoided in future. So I do not know how long it will take to have such a system in place. Fortunately, in railways, we have got a system where we can control the overloads over the bridges. Any new rolling stock that we introduce, we get the first clearance from the RDSO and the concerned zonal railway CB. So we are able to control the overloads. And if any rolling stock is having parameters heavier than the design parameters of the bridge, then we impose the speed restrictions. Unfortunately, in road sector, this is not possible. So this is a serious matter. We should look into this direction also. How can we have this kind of a legal sanction on the bridges? So regarding earthquake, Mr. Vinay Gupta has spoken about it. Let me tell you, I have seen a bridge in NF Railway. It was built some 100 years ago. There was a failure because of a derailment, and I had the occasion to visit that bridge. Not only the superstructure, even the substructure was made of steel. It was made on steel trestles, you know. And it was a wonderful bridge. It has given a service life of more than 80, 90 years by that time. So we have to change our way of thinking in favor of steel bridges and steel substructure also. I think the time has come to do a realistic assessment of the thing, where we are and how can we move ahead. Thank you very much.
Thank you, Ravindra, for your words. Vinay, if Atul, you've got the questions in front of you probably.
Yeah.
Could you take the ones you want to answer? That would probably be the easiest way. Read them and answer them, which ones you like, and add whatever, you know. And if anybody else in the panel wants to say a few words on each question after Atul, give a pause, let them say it, and move ahead. Take them in the order you want to answer, you know.
Yes, Atul Bobe, if you are able to see the questions yourself.
Yeah.
Yeah, nothing like it.
So a couple of people have asked what are the specialities of weathering steel. I had already answered that question when Vinay asked me this question. How is this steel different from conventional steel? Many people wanted to know that. I think we have already answered that. Couple of people have asked how and where was the debris disposed. So as part of this bid, a specified yard was given by the state PWD, was identified and given. So what's being done now is that cut-off segments have been transported using conventional vehicles to this yard, and then they have been crushed at that yard. Further, that crushed material has been used in the embankment of this same highway, which goes all the way to Hajipur. So the crushed material has been used as base material. And then, of course, there's GSB and so on. All the other crust has been constructed on top of that. So a lot of this material has been reused. Steel, of course, has been sold as scrap. So you cannot really reuse that steel. So that is that. Whether any future pre-stressing blisters were available in the old superstructure, Mr. Venugopal wants to know this. No, there were no future pre-stressing blisters. Remember, this is a bridge that was designed in the 70s, and there was no such thing as future pre-stressing at that time. Unfortunately, no future pre-stressing blisters were available. Mr. Venugopal, okay, he's got one more question. When the cantilever footpath is removed, the free body diagram changes. Any evaluation is done for existing piers? No. The cantilever footpath does not change the free body diagram. The box section is the only one that is pre-stressed. The cantilever footpath has been added later on as a dead load. So there's no change in the free body diagram. And of course, evaluation was done for the existing piers by removing the load. And that's one of the conclusions that we reached is is that the piers were quite safe to carry the load. Mr. Dipendra Bhaumik wants to know what is the main reason of early failure. Is it failure of post-tensioning or central hinges? Was it primarily an improper assessment of the losses or behavior of the central hinges? So I think in one of my slides, I already explained you cannot pin this on one particular reason. There are multiple reasons why this happened. So it could be that the hinge started failing first, or the post-tensioning had very high losses compared to the losses assessed at the time. But one thing we know for certain is that the losses as estimated in the 70s were definitely on the lower side. This is a fact that is known now after 50 years of that happening. So we are sure that the losses were improperly assessed. I would not say improperly assessed. They were assessed as per the code of that time. But okay, the code itself was assessing the losses on the lower side. So I guess it was a multiplicity of reasons why it actually failed.
I think it's a combination of many reasons together that has led to this failure.
Yeah, absolutely.
Corrosion.
And I repeat again that there was absolutely nothing wrong with this design. This was one of the most innovative designs of its times. We must record that this was one of the really innovative designs. It had precast segmental construction, non-glued together with a central hinge in the 70s. Something that we dare not do even today.
I want to tell you, Atul, I was only 18 or 19, and I spent 2 months of each summer holidays on this bridge project. Mr. Nanjangud and his wife were there at that time. I actually stay with them. And I worked on this project myself, for 2-3 months. All the drawings, everything, I learned a lot on this project. It was way ahead of its time.
Yeah, absolutely.
Way ahead of its time. Only at that time, we didn't have the state of knowledge that we have today. So it's a classic situation of upgrading your knowledge level. You make mistakes, you learn, and you try to prevent them from happening again. Absolutely. And what you've learned probably finds its way into coded changes, which has happened a lot in this new 112 code. You see a lot of changes that are there to address things like shrinkage, creep, long-term effects of concrete, very poorly understood. Doing away with low relaxation steel as the steels to now have only low relaxation steel. Doing away with that, which gives you about 6-7% loss straight away, which is a hell of a lot of amount. Then doing away with these central hinge bearings, which were plunger type. The modern central hinge bearing is a great innovation. And that is usable on extradosed bridges, usable on such balanced cantilever bridges. There were a whole family of these bridges built at that time, okay, all over the world.
Yeah,
and
absolutely.
About 90 of them, and all of them suffered this kind of distress to various degrees.
Yeah.
So these are we learn by our mistakes as engineers. Nothing is perfect when you start out. But if you don't try, you will never get there. You will never innovate. So at that time, it was a leading class innovation. And we learned the mistakes, and over time, we'll overcome them. So there is a case maybe to go back for that structured type with these modifications and state of knowledge today. But there's also the other hand that why not do it in steel if we can get long life and sufficient balanced life from steel? Why not do it in steel for the various advantages that others have spoken about today? Go ahead, Atul.
Yeah. So Mr. Devjyoti Paul wants to know what is your view on estimation of creep in calculation of the observed value of deflection. So, okay, almost everybody has answered that already. Mr. Beno D'Souza says JSW has supplied 700 tons of corrosion resistant weathering steel for Patna Museum, which was supplied and used successfully. JSW weathering steel was tested and approved by a Japanese consultant in coordination with Indian architects. So I think this is more of a comment. Thank you, Mr. Beno D'Souza, for that. Ahmed Usama Sayed says, as we are discussing the replacement of old bridge decks, what is the scope and future of replacing concrete decks with all FRP bridge deck as it is done in US and Europe? Okay, that's a good question. I think we are still a decade away from doing that straight away in India. I'm not sure if we are ready to use FRP bridge decks in India straight away before they are proven in US and Europe. We do ourselves a lot of innovations, as you must have realized. When we do these things, we don't even realize it's an innovation. What today is being used on cantilever construction, extradosed bridges as a needle beam was what we had proposed a decade back, even without knowing that it's called a needle beam. Okay, we didn't know that it's called a needle beam at that time, but we had proposed a similar solution. So, you know, great minds think alike and so do fools. So I guess it depends on who's thinking of what at a particular given time, I think.
May I would just like to add.
Yes, Mr.
We,
Puri.
you know, the committee which is at the moment working on a code on FRP, we are not still allowing on the superstructure.
Yeah,
So just for
absolutely.
information.
Absolutely. Thank you, Mr. Puri. So Professor Mainak Ghoshal, Mr. Tarun Mathur, everybody is asking about specification for weathering steel and its welding. I think if you just do a Google search, you will get a lot of information on this. I don't want to go into details here. It will take too much time.
Very true.
Can you explain the negative side while dismantling the pre-stressed box girders, Dr. Narayan Tiadi? I don't quite get the question. I didn't quite get the question. There's no negative side of dismantling the pre-stressed box. I mean, okay, it's a challenge, is all I can say. I mean, if you are able to do it properly, then you should be able to dismantle it. Does weathering steel usage seem more suitable in humid area as the possibility of rusting is higher there? Parth Samria is asking this question. Yes, absolutely right. Weathering steel usage is obviously more suitable in humid areas where corrosion resistance is required. Here, the possibility of rusting is a little low. The Ganga, unfortunately, now doesn't flow in 6 kilometers. It flows only in 300 meters or 400 meters of width. It's dried up for most part of the year, except just after monsoon, where it is actually in spate. And at that time, it spreads over 6 kilometers. But otherwise, for most part of the year, let's say almost 8 months in a year, you can almost walk across the 6 kilometers from one end to the other, except for maybe a small part, which is navigational. Mr. Bandhu wants to know whether it is a pot bearing or a pot cum PTFE bearing. Well, it is a pot cum PTFE bearing. I mean, there's no pure pot bearing as such now. These days, when we say pot bearings, we mean pot cum PTFE.
I have another question on weathering steel. Is there any specification or requirement of having an additional thickness over and above the design value?
No. See, the weathering steel first of all, for weathering steel, we have no separate code. At least in IRC, we have no separate code. IRC does not differentiate between grades of steel. IRC gives you all grades of steel, but the rest of the code is all the same for all grades of steel. So it doesn't really differentiate between the two. So you could be using 410, you could be using 450, you could be using 350, you could be using stainless steel. All steels are clubbed under one code as far as design is concerned. And compare that with the material specifications. Every material has a different code, whether it is IS, IRC, or IRC, of course, doesn't have material codes. But if you go to the relevant IS code or to the ASTM, then you can get a specific code for almost every specific material that you're using. But these are more material specification code. They are not design codes. Fortunately or unfortunately, the design is governed by the IRC code, at least in
as
India.
far as because these are not available in Indian code, as far as German or any other code. Because whenever we go to Germany or
almost all international codes don't ask you to provide any additional thicknesses as far as weathering steel is concerned. The most common place where this is used is the UK, some parts of Middle East, and Japan. Of course, it's extensively used. They have perhaps one of the most extensive literature available on weathering steel, by and large. We did a lot of research at that time, 10 years ago, when we wanted to use weathering steel. Okay.
Just one second, Mr. Ulabje, you're there in the panel, sir. Do you want to say something about weathering steel and stainless steel, and do you want to talk about anything by unmuting?
Yeah, good evening, everybody, and it's been my pleasure to learn from Mr. Bove. Thank you for an excellent and enlightening presentation. And thank you, Dr. Harshvardhan, for facilitating this along with your entire team from IIB. A big thank you for that. No, I would just like to suffice to say that the innovative case study, and Mr. Bove said that the design itself was innovative. to start with, but I think the solution was even more innovative, to refurbish and create a new bridge out of the old substructures. So heartiest congratulations for that. And rather than talking too much technical on the subject, I would like to say that JSW Steel is gearing up with massive expansion plans in Dolvi as well as Vijayanagar to support these kinds of initiatives going forward and help all of you who are working to bridge the infrastructure deficit which is there in India today in the best possible and innovative manner using steel solutions. So I assure you that going forward, we'll be supporting the infrastructure industry in a much bigger manner. Thank you.
Thank you, sir.
Sir, we have an assurance for the next replacement of a bridge with steel. You will get good quantity here.
I'm going to take two more
ahead,
questions.
Ashish.
I think I see two more questions here.
Ahead.
Mr. Pratyush Jha is asking, can we integrate spine cantilever construction in steel bridges? Absolutely, you can. There's nothing stopping you. And like I always say, necessity is the mother of invention. When we started looking at replacing the superstructure, we didn't really start by saying that we want to replace it with steel superstructure. It was only after we had exhausted all other options that we said that, okay, this is now the best option. So if you heard me carefully during the presentation, I said that we started out by doing a do nothing option. What would happen if we did nothing? Don't spend anything at all and try and see what's the balance life of the structure, right? I think that's the starting point. And then you end up by saying that, okay, you are not able to sustain the structure. And so we don't really start with sustainability, circular economies, environmentally sustainable designs and all that. You start with the very basics. And then, okay, all the other factors get automatically built around your solution. It's you would be putting cart before the horse if you go the other way around, I think. Any dampers used for steel superstructure in reference to the revised seismic behavior for truss bridges against the balanced cantilever bridges? Mr. Devendra Manganani is asking this question. No, no dampers were required to be provided for the steel superstructure. I think that's about all the questions that I can see, unless I've missed something. I think I've answered almost all.
Ruhi, if you are there, Deepika, if you're there, Mr. Ashok Basa is in the audience. If he is still there, Mr. Ashok Basa, can you unmute him? If he's in the audience, B-A-S-A.
Yeah, he's there.
Ashok, can you kindly unmute him, ma'am?
At least I can see him.
Deepika, could you unmute Mr. Ashok Basa?
Just a second, sir.
Right. Just before this, Mr. Basa joins, he was the past president of the Institution of Engineers. He is part of our Steel Bridges Committee, and he and another gentleman, Gyana Mohanty, who is, I also have he's in this audience. I would like his views. They have done a lot of work in steel. And Mr. Basa, if you're there, I can't hear or see you. Can you unmute yourself?
No, he has to be part of the panel for him to speak.
You have to upgrade him to panel, no?
Yeah, I don't think he can speak directly from
I just did him. I don't know. I just did him.
Okay, Basa Sahab, can you hear us all, and can you say a few words?
No, he has to be on the panel for him to talk, I think.
Yeah,
yes, he's there. You have to unmute, Basa Sahab. You have to unmute.
Ah, there he is.
Left unmute. Left side unmute.
There he is.
Yeah, we see you, Basa Sahab. You have to unmute yourself. Basa Sahab, you have to unmute.
Oops. I don't think he is.
Okay. I just want to share some wonderful news with all of you all here. And I was hoping he would be on screen when I did that, if he's having some difficulty. Mr. Ashok Basa has been made the president of the WIFO, the World Engineering Federation, the first ever Indian to have become that.
Congratulations.
It's a federation
Wow.
of all engineers, of all engineering institutions of the whole world.
Fantastic.
And he's the only Indian to have achieved that distinction. It is something remarkable. And I would like to salute him here. With you all, I would like to salute him and give our
Fantastic.
absolute appreciation to a phenomenal task achieved. So if we can't have him here, at least he can hear us. So
Yeah.
appreciate that. Okay, with that, I think if there's nothing to be added, Puri Saab, anyone, Mr. Pandey, anybody to add any words, please feel free. Otherwise, we should be closing in the next 2-3 minutes.
We can only say wonderful and keep it with more and more such presentations. We help everybody.
Thank you, Puri Saab. Thank you so much, sir. Thank you so much.
On behalf of JSW, I thank all panelists and Mr. Atul Bhobe, Dr. Harsha, Mr. Vinay Gupta for disseminating such wonderful knowledge to the all stakeholders. Thank you very much for that. And
Thank you.
I also thank all participants.
Thank you, sir.
Thank
Yeah,
you,
Vinay.
everybody.
Vinay, last word for you.
Yes,
And
before we end, I think the life still must go on, and it does go on. So this is about the next lecture that we have. I mean, of course, I'm assuming that we are into close of the previous, today's lecture. So we have a lecture on a very different topic, that is use of external pre-stressing by past president of IAS Trustee, Mr. Alok Bhaumik, which will take place on the Friday, 8th April. So please do join in. And that's all I wanted to say. Thank you so much. But thank you so much, Dr. Harshavardhan and Mr. Atul Bhobe. All of you, both of you have done a great job today. And Deepika or Ruhi, anybody is there? Would anybody like to propose a word of thanks?
Yes, sir. Ruhi will be doing the word of thanks.
Okay.
I'm not seeing her.
Ruhi, are you with us? You are muted. So, Deepika, all yours in that case. Deepika?
Yes, sir. Just checking. Yeah. Hello.
Yeah. Yes.
I'll just propose the vote of thanks on behalf of Ruhi. Just a second, sir. Thank you, sir, to all the respectable dignitaries. It's my privilege to have been asked to propose a vote of thanks for our 6-month webinar series on Steel Bridges Day 2, sponsored by JSW Steel Limited. I, on behalf of IIB, extend a very hearty vote of thanks to all the members and non-members for gracing us with your presence and sharing with us your valuable feedback and suggestions. Firstly, I would like to thank our Director General, Engineer DG Divte, for always providing us with a vision for the future of IIB. Our President, Engineer Vinay Gupta, for constantly guiding, motivating, and inspiring us to achieve the vision. I would like to thank our Treasurer, Mr. P.R. Kelkar, for being a strong support of IIB. Our Honorary Secretary, Dr. Gopal Rai, always guides us with his humorous side. Our Honorary Secretary, Engineer Swapnil Joshi, for always managing this platform. I would like to thank to our today's speaker, Engineer Atul Bhobe, for his enlightening and entertaining presentation and sharing valuable knowledge on this platform about MG Setu. It was quite insightful. I would also like to thank our today's moderator, Dr. Harshvardhan Subbarao, for managing the webinar on this forum and also for providing so much of information. I would like to thank to all our eminent executive committee members and Shri S.K. Puri for their valuable presence and support. I would also like to thank our coordinator, Ruhi, for coordinating and always managing the event to make it happen always on time. And last but not the least, I would like to thank Mr. Josefa for all his IT support. Thank you, everyone.
Thank you.
See you guys soon. With that, we close today's session and hope to see you in the next one, the Friday of the 8th and in the next. Thanks, Atul, once again.
Thank you.
Have a pleasant evening, all. Have a pleasant evening.
Thank you, everyone.